So, can you help me with this? So with the annotation, because when that's not.
You want to annotate on it?
Cannot really go.
So you can cross it?
And then just. I was just gonna.
Dr. Jimmy, you want the pointer?
I know, I want the.
You want to draw it?
Draw. I want to keep drawing while drinking. Okay, well then I want to make.
Yes.
So I have to click on the mouse.
You have to, yes. You have to clear the line.
Okay, cool. No worries. Okay. Okay, assalamu alaikum. Okay, good afternoon. Good day, good morning. We have lectures now in the afternoon. So welcome to the neuroscience block. I hope you will have a good time. My name is... so everyone is... do you hear me in the back? You do? Okay. So my name is Abdullah Alshawaf. Okay, I'm a member of the Department of Physiology. So I will be teaching you, Dr. Hamdan and I will be taking care of the physiology lectures in the neuroscience block. So please, if you have questions or concepts to clarify, please, you can send an email. So you can find my email here. We can also arrange time to answer your questions if required. Okay. So the first lecture of the physiology is on electrical properties of excitable cells. So I guess you guys already been exposed to action potential, membrane potential in the first year, isn't it? So this will be like a refreshment, and because this is the neuroblock, so we have to talk about the electrical properties of neurons. Okay. So basically the outline of my lecture will be, so firstly we'll talk about the laws that govern the movement of ions. Okay. Then we'll talk about the resting membrane potential. Okay. Then we will talk about action potential and the propagation of action potential. And finally, we'll talk about, we will compare graded potential with action potential. Okay? Just check. No, I was just speaking. Okay, so let's start. Okay, so firstly, I would like to introduce some simple electricity concepts, because we will be talking more about voltage, current, conductance. What do they mean? Okay. So, and a simple analogy, or in order to understand these concepts, is we will use the battery. Everyone uses a battery. Yeah? You guys are familiar with the battery? Of course, okay? So a battery has two ends, as you can see here. So it has two ends. So here we have the positive end, which is called a cathode, okay? And a negative end, which we call anode, okay? And a battery has a electrical potential because in the battery we have electrons, which we are forcing, okay, to stay in the negative end, okay? And so this is how we create an electrical potential or voltage, okay? So if we connect the negative end with the positive ends by connecting a wire here, okay, which is conductive, what's going to happen is that these electrons, because they are negative, they are attracted to go to the positive end, isn't it? And so the movement of these electrons to go to the positive end is basically what we call current, okay? And conductance is simply how easy it is for these electrons to reach the positive end, okay? Resistance is the opposite. It is how difficult it is for these electrons to reach the positive end. Is this clear? So voltage is, as you can see here, is measured in volt. Current is in ampere, okay? So one way to measure the electrical potential is by using a device called voltmeter, as you can see here. So this battery has a voltage of 1.50 volts, okay? Okay. So the relationship between the voltage, current, conductance, or resistance can be described by Ohm's law, which states that current equal voltage over resistance. So what does this mean? It means that the bigger the voltage is and the lower the resistance is, the bigger is the current, okay? And this can be, explained in this way, where you can see here, we have a water tank, okay? We have a water tank. And so height can represent voltage, okay? And the pipe, the diameter of the pipe here, okay, represent the resistance or conductance, okay? And current is the flow of water. And so here in the middle, you can see that the bigger the voltage, the lower the resistance, we will get what? More current, big current, very good. Whereas in here, okay, we have high resistance, and so we have what? Lower current, okay? So this is just to show you the relationship between current, voltage, conductance, or resistance, okay? Now, so every time I have to do this. So what was amazing is the discovery that cells have electrical potential, some cells, okay? So this was discovered in the 1940s. Wow. Okay. So this was discovered in the 1940s by these scientists, Hudkin and Huxley, who they showed that neurons, okay, from squid, okay, what they did is basically they inserted a microelectrode inside neurons, okay, which was connected to a voltmeter, and they showed that these neurons, they do have electrical potential, okay, and so these type of cells are said to be excitable, okay, including neurons and muscles, okay, and so while at rest, these neurons, when they are not excited, are said to be at rest. So they have a resting membrane potential, okay? And the resting membrane potential usually correspond to negative 40 millivolts to negative 90 millivolts, okay? And so these cells are excitable, so it responds to a particular stimulus, okay? They can transiently reverse their membrane potential into a more positive values, okay? So as you can see here, so the resting membrane potential, let's say, is negative 65 millivolt, okay? So it responds to a stimulus, and if the stimulus is big enough, the membrane potential will be taken more into a positive value, reaching a particular threshold. If it reaches the threshold, then it will transiently reaches less negative values or more positive electrical potential, only for milliseconds, and then go back to the resting state. Okay, is this all clear? Any questions so far? Okay, good. Now, okay, so basically what contributes into the electrical potential of in cells is the movement of ions. So with electricity, it's the movement of the electrons. Whereas in cells, in excitable cells, it is the movement of ions that is responsible for the generation of the electrical potential. Okay. And so why the movement, why there is an electrical potential, why do ions move? It's because there is a concentration difference, okay, both inside to outside the cell, okay? And in addition to the concentration difference, there is channels which are selective to particular ions than to other ions. This is very general introduction, okay? We'll go into more details in a second. And so this difference in the concentration and the selective permeability is due to the existence of selective ion channels as well as active transporters. Okay, so we know that we have active transporters like the sodium-potassium ATPs, which transport ions down, or is it against concentration gradients? Against concentration gradients, very good. And we have ion channels, which are selective to specific ions than to others. Okay, so this is just very general overview. Okay. Now, let's focus on the resting membrane potential, on how it is established. We said what's responsible for the electrical potential is the movement of ions. Okay. I would like to welcome Dr. Hashim. He's a professor of physiology, and he's our chair of physiology. So, okay. So I would like to focus now on this part, on the resting membrane potential, okay? And we said what contributes to the generation of the electrical potential is basically the movement of ions, isn't it? And so the most important ions, so the most important ions that are responsible for the generation of electrical potential is potassium, okay, which has a higher concentration inside the cell compared to outside the cell, okay? Also sodium, which is the opposite. It has lower concentration inside the cell and a higher concentration outside the cell. Okay? Also important is calcium, but we will see in the second lecture when we talk about synaptic neurotransmission. And as you can see here, it has the lowest in the cytosol of the concentrations, and it has a higher concentration outside the cell, okay? So these ions, specifically potassium and sodium, are very important for the generation of the electrical potential, membrane potential. Now, we said when neurons are at rest, they have a membrane potential of what? Which value? Negative 65 millivolt. Okay, so what does negative 65 mean? Negative means that it has more negative particles inside the cell compared to outside. But what does this value really mean? Okay, basically, let's take this scenario here. Okay, so let's take this scenario. As you can see here, we have these two compartments. So this is inside the cell and this is outside the cell. And we said potassium is highly concentrated inside. Okay, so we have a higher concentration of potassium inside and a lower concentration of potassium outside. Now, as you can see here, we have a membrane, and this membrane is not permeable to potassium. There are no channels. So what do you think is going to happen? Would there be movement of potassium? There wouldn't be movement of potassium, okay? Now, if we start inserting ion channels which are selectively permeable to potassium, where does potassium, what's going to happen to potassium? It will be moving from where to where? From inside to outside. Why? Exactly. So there is a diffusion force forcing potassium to go from the higher concentration into the lower concentration. So from inside to outside. Now, as potassium moves from inside to outside, okay, the inside of the cell gains negative charges as it loses positive charge, which is the potassium, okay? And outside is gaining more positive charges. And so at some point, potassium will be starting to get attracted to go inside. So the electrical force, okay, will start moving potassium to the inside, but it will be counterbalanced or will be counterbalancing with the diffusion force. And so potassium will stop moving, okay? And so when potassium stops moving, we can say that it has reached an equilibrium potential, okay? So this is the equilibrium potential for this particular ion, which is potassium. So no net movement of potassium will happen, okay? So this is what we call what? Equilibrium potential for potassium. Good. Now the equilibrium potential can be calculated by a formula, by an equation, which is called the Nernst equation, okay? Which basically, it is the following. So equilibrium potential for a particular ion equals 2.303 times RT. R stands for gas constant. T for absolute temperature. Z, which is important, is the charge of the ion, whether it's positive or negative. And F is a constant. So log the concentration of the ion outside over inside, okay? This may look complicated, but it's actually not. So if you calculate this, so if we calculate the constant values, we will end up with 58, okay? And so the equilibrium, so in this case, let's say we have inside 10 millimolar of potassium, and outside we have 1 millimolar of potassium, okay? Now, if we want to calculate the equilibrium potential for potassium, it would be 58 over the charge of the potassium, which is what? +1, times log the concentration outside over inside. And so outside is 1 millimolar over inside, which is 10. And so we'll end up with negative 58 millivolt. And so a negative 58 millivolt with this hypothetical scenario is the equilibrium potential for potassium, where at this particular voltage, potassium would be stopping the movement, okay? And so if the concentration of potassium So if the concentration was 10 in the inside, it would be negative 58. If it was 100, it would be negative 116 millivolt, okay? So can you give it, sorry. So can you give a shot at calculating the equilibrium potential for sodium given these concentrations? Anyone? It's very easy. So the concentration of sodium outside is 10 millimolar and inside is 1 millimolar. Yep. Very good. Excellent. It's positive 58 millivolt. Excellent. Very good.
Doctor?
Yes.
58 is the constant number, right?
Yes. Okay. Now, how is this related to the resting membrane potential? So now we know how we calculate the equilibrium potential for specific ions like potassium and sodium. And so let's take real concentrations, okay? So here we have the real concentrations, okay? So, okay. So when we calculate the Nernst equation, what we will get is that the equilibrium potential for potassium would be around negative 84 millivolts. And for sodium, it would be equals to positive 67 or so, okay? Now, if the membrane was only permeable to potassium, the resting membrane potential would be equals to the equilibrium potential for potassium, okay? If it was only permeable to sodium, the resting membrane potential would be equal to the equilibrium potential for sodium. And so if it was only permeable to potassium, it would be around negative 84 millivolt, the resting membrane potential. If it was only to sodium, it would be positive 67. But in this case, we know what if it was permeable to both, but highly permeable to sodium? What do you think the resting membrane roughly will be around? Is more positive, very good, closer to the equilibrium potential for sodium. If it was highly permeable to potassium, where would it be? Closer to the equilibrium potential for potassium, which is, in this case, we know that the resting membrane potential for neurons is around negative 65 millivolt. So what does this tell us? Very good. So it's more permeable to potassium. It's closer to the equilibrium potential for potassium, okay? And so because the membrane is selectively more permeable to potassium, okay, this is why the resting membrane potential is very close to the equilibrium potential for potassium. And also active transporters, which tend to concentrate potassium in the inside, play an active role in, into establishing the resting membrane potential. And this is what scientists did by increasing so they did an experiment where increasing the concentration of the potassium in the extracellular media and the outside of the cell tend to bring the membrane more into a positive value, okay? And so this is how the resting membrane, basically the ionic basis of the establishment of the resting membrane potential. There is another formula, which is called the Goldman equation. We won't go into details with the Goldman equation. It's basically to calculate the membrane potential itself, not the equilibrium potential, okay? The membrane potential, and so it will take into consideration all the concentrations of the ions inside and outside, okay? And so given what we explained, at the resting state, basically it is at negative 65 because it has a higher permeability to potassium than other ions. And so it's closer to the equilibrium potential for potassium, okay? Any questions so far? All good? Okay, so that was the resting membrane potential. Now we'll talk about the action potential. Okay. So as we said, that the most important ions responsible for generation of the electrical membrane potential is the sodium and the potassium, okay? And so here I would like to explain a few terminologies, okay? So we said the neuron here, the membrane is at rest, which is, it could be between negative 65 around to negative 90 millivolts or so, okay? And so this is the resting membrane potential here, okay? Now, and here, when there is a stimulus, we said that neurons are excitable cells. So it responds to a stimulus that will open sodium channels, okay? Opening sodium channels and entry of sodium would take the membrane into a threshold, okay? So if it reaches, the electrical potential reaches a threshold, okay, what will happen is that the membrane conductance to sodium increases dramatically, okay? And here we say this is the upstroke of the action potential. We can say that the membrane is depolarized. So depolarization, meaning that the electrical potential is going into a less negative, more positive values, okay? And so in here, this is the overshoot of the action potential, where there would be inactivation of the sodium channels and opening of the potassium channels, which we will describe in details in a second, would repolarize the membrane. So repolarization meaning that the membrane potential would go where? Into more towards more negative values. Very good. Okay. And this part here is called hyperpolarization, or the undershoot is being more hyperpolarized than the resting membrane potential. Okay. Now so what is really the ionic basis of the movement of sodium in the action potential? Because we know here that when the voltage-gated sodium channels open, okay, as we will see in a second, there will be a dramatic inward current of sodium, which will bring the membrane into a more positive values. Why? Okay, and this can be basically described by what we just covered in the introduction. Yep. Sorry. Okay. So this will be basically described by the law that we covered in the beginning, which is the Ohm's law, very similar, okay? So basically current equals conductance times voltage, which is in this case is the ionic driving force. So in here, so this is the current for the specific ion of interest. Conductance basically is, we said, is how easy it is for the ions to move, or the electrons. And in this case, it will be represented by opening of the channels, okay? If the channels are open, then this means that there is high conductance for this specific ion, okay? And now this is the ionic driving force, which basically is the membrane potential minus the equilibrium potential for this ion. So this means that the ions will move as long as the membrane potential is not equal to the equilibrium potential for that ion. Is that clear? So if the membrane potential was the same as the equilibrium potential for potassium, will there be any movement of potassium? No. It will be no movement of potassium, and so there will be no current of potassium. So potassium or sodium will always move as long as the equilibrium potential, the membrane potential is not equal to their to their equilibrium potential. Okay, is this clear? So let's take this example in here to clarify this concept. So let's take this example. So this is a cell, okay? And so we said that inside the cell, we have a higher concentration of potassium, okay? And lower concentration of sodium. Now we know that the equilibrium potential for potassium, so the equilibrium potential for potassium is negative 80 millivolts, okay? Now, in this example here in A, there are no channels open. And so the conductance for potassium would be equals to 0. And so if we fill in the formula that we have, okay, basically the conductance is 0, okay? The membrane potential is 0, as you can see here, so it's 0, okay? And the equilibrium potential for potassium is what? Minus 80. Very good. So what is the ionic driving force in this case? Negative 80, then it would be positive 80. Very good. So it is positive 80. So what this means is that there is a huge ionic driving force for potassium to move, but it doesn't move because there are no channels open. Conductance is 0. Plus 80 times 0 would be equal 0. So there would be no current. Is this clear? In this case, when we start opening the potassium channel, okay, what will happen is that the potassium will start moving out, okay? Anyone, why potassium is gonna move out? But why not in? Because of the concentrations. Very good. The reason why potassium wants to move out, because it is moving in the direction that it will take the membrane potential to its equilibrium potential. So the equilibrium potential for potassium is what? Minus 80, exactly. So by potassium, which is a positively charged, by moving out, it wants to make the inside of the cell more negative, okay? And so this is why it's moving out, because it wants to reach the equilibrium potential for the potassium, okay? Is this clear? Okay, good. And a trick that you can use to identify whether the movement is inward or outward in the case of cations, like sodium or potassium, when you calculate the ionic driving force, if the sign is positive, it means it's outward, okay? When you calculate the ionic driving force, if the sign is positive, it means it's gonna be an outward movement. If the sign is negative, it means it's gonna be an inward movement, okay? This is in the case of the cations, whereas in the anions, like chloride, it's the opposite, okay? Now, so this is basically what I just described, okay? And so in the action potential, okay, we know in the resting state, it is negative 80 millivolt because it is highly permeable to potassium. There is high conductance for potassium. This is why it's closer to the equilibrium potential for potassium, okay? When the voltage-gated sodium channels open, there is high ionic driving force for sodium to go to the inside in order to bring the membrane to its equilibrium potential. And so this is why there is a huge inward movement of sodium to the inside, okay? And so this is how the membrane will depolarize, okay? Repolarization is by higher conductance for potassium, as we will see, okay? Now, another huge factor in this case is the channels, okay? For example, we know that because of the opening of the voltage-gated sodium channels. So, for example, we know that when in action potential, usually the overshoot reaches which value? Do you know? Do you remember? It's around plus 35, okay? Why doesn't it reach the equilibrium potential for sodium? Very good, excellent. Because of the property of the voltage-gated sodium channels, okay? So they do, because they represent conductance, okay? Without them opening, there would be no conductance, okay? So basically, one of the properties of the voltage-gated sodium channels is that they activate when the membrane is at threshold of negative 55 millivolt, okay? And they become inactivated when the membrane reaches a value of positive 35 millivolt, okay? There are also other channels which are mainly responsible for the synaptic. We will explain tomorrow about the synaptic neurotransmissions, which are the ligand-gated ion channels, okay? So the difference is that the ligand-gated channels require the binding of neurotransmitters, whereas the voltage-gated channels, they are sensitive to changes of voltage, of the membrane voltage. Is this clear? Any questions so far? Okay. So let's put all the pieces together, because we explained few concepts, but they are all over the place, isn't it? So let's make it one whole image. Now, so this is an action potential, okay? So at negative 70 millivolt, what do we call this? When the membrane is at negative 70 millivolt, this is the resting membrane potential. Why it is negative 70 millivolt? Because of the high permeability to potassium, which makes it closer to the equilibrium potential for potassium. Good. Now, when there is a stimulus, okay, and we have an opened ligand sodium channels, okay, and they allow the entry of sodium to the inside. And now the membrane has reached the threshold. Now we have opened which ones? The voltage-gated sodium channels. Opening of the voltage-gated channels would allow what? Sodium to enter to the inside. Why it does enter to the inside, not to the outside? Because, very good, but mainly because of the huge ionic driving force for sodium to go to the inside of the neuron, okay? And so it goes to the inside in the direction that it wants to take the membrane to its equilibrium potential. But does it reach the equilibrium potential? It doesn't. So it only reaches around positive 35 millivolt. Why? Because sodium voltage-gated channels would inactivate at the overshoot. At the same time, there would be an opening of the voltage-gated potassium channels, okay? Opening of the voltage-gated potassium channels would enable potassium to go outside or inside? Outside. Why? Because of the huge ionic driving force, which is, if you calculate it, it would be positive, that would, make the potassium wants to take the membrane to the equilibrium potential for potassium. Now, in this part of the action potential, you can see that in this undershoot, that the membrane has reached an even more negative values. Why? Very good, because it even went very close to the equilibrium potential for potassium. Okay? It went very close, approached the equilibrium potential for potassium, but because of the sodium potassium ATPs that would concentrate potassium to the inside, it will stabilize the membrane potential to the resting state. Okay? So is this clear?
Doctor,
Yes.
in the previous slide, the resting membrane potential was negative 80, which is the equilibrium potential for potassium. How, if it was negative 80, what is the hyperpolarization?
So, like I said, there are variations between neurons in terms of measurements. So it depends on the concentration of potassium. So it's not going to be that the equilibrium potential for potassium definitely is not going to be equal to the resting membrane potential. It's always more negative than the resting membrane potential. Okay. Any more questions? Okay. Okay, so this was the action potential. So what I want to point out in here is that in this part of the action potential, okay, so this part of the action potential, this is called the absolute refractory period, where no matter what, how big the stimulus is, the next stimulus, there would be no generation of another action potential. And the reason for this is because of the inactivation of the sodium channels, okay? Because sodium channels, we said, they inactivate around in the overshoot, and so they require some time before they allow activation again. And so this part of the action potential is the absolute refractory period, so there would be no generation of another action potential. Whereas in this part of the action potential, it's relative refractory period, okay? There is the action potential can result, okay, in response to a next stimulus, but a bigger potential or a bigger stimulus is required in order to take the membrane to the threshold, because now, as you can see here, that the membrane is even hyperpolarized. It's more negative than the resting state. And so a huge effort is required in order to take the membrane to the threshold in order to generate another action potential. Okay? Okay. So this is just explaining the absolute and the refractory. So some of the properties of the action potential is that it's initiated by depolarization, so in response to a stimulus, okay, an external stimulus, okay, that would, as we will learn in the synaptic neurotransmission, open ligand-gated ion channels, which if the potential is high enough and reaches a threshold, it will lead to the generation of an action potential. The action potential is all or none phenomena, which is it happens or it doesn't happen, okay? And also it has a constant amplitude. So the amplitude of the action potential, as you can see here, this is the amplitude, it doesn't change, okay? There is high frequency, it does get more frequency in response to a stronger stimulus, but the amplitude doesn't change, okay? And also action potentials don't add up. They don't summate in order to generate a greater action potential, no, okay? These are some of the properties of the action potential. Okay, so now let's talk about action potential conduction. Any questions so far on the ionic basis of the resting or the action potential? Questions? Okay. So let's talk about conduction of the action potential. So as I said, so we have neurons in here, So as you know, that neurons have cell bodies, they have dendrites, and this part of the neuron is called what? Axon. Very good. And so basically a neuron would receive, hundreds, tons of discharges on their dendrites. Now, receiving these discharges, okay, if they were big enough, okay, to take the membrane at this area here to threshold, then there would be a generation of an action potential. So this zone, okay, of the neuron is called the axon hillock, which is the trigger zone for action potential, okay? And this trigger zone, what's special about it is that it does have concentrated voltage-gated sodium channels, okay? Is this clear? Is this clear? Good. Now, okay, as the voltage-gated sodium channels open in the axon hillock, okay, there will be depolarization of this part of the axon, okay, in the beginning, okay? And so depolarization then will be followed by the opening of the voltage-gated sodium channels, will be followed by repolarization by what? So of the potassium channels, okay? So it's like a cycle. So depolarization, opening voltage-gated sodium channels, followed by repolarization by opening the potassium channels, okay? And so the action potential would propagate in the same way, but it doesn't go back. Why the action potential doesn't go back? It's always unidirectional. Why? Sorry? Because of the refractory period. Very good, excellent. Because of the absolute refractory period, where the sodium voltage-gated channels are inactivated, okay, this does not allow the action potential to go back. It always just moves forward, okay, down the axon. And it's like the burning of the fuse, okay? And so factors that influence the conduction velocity, the speed of the action potential, is the diameter of the axon. The bigger the diameter of the axon, the faster the speed of the conduction of the action potential. So you can see here we have different types of axon. They have different diameters. So in this case, the A alpha type, they have big diameter. So the conduction of the action potential is fast, okay? Whereas the C type fiber have a smaller diameter, and so the speed is slow, okay? The other factor is myelination, okay? So myelin sheaths wrapping around the axons, okay, which are made by which cells, do you know? The myelin, the Schwann cells, or the oligodendrocytes, okay? So these myelins, they do help in the speeding up of the action potential by concentrating the sodium voltage-gated channels in the node of Ranvier, okay? So you can see here an axon where there is a myelin wrapped around it. And so here in this areas where there is concentrated voltage-gated channels, this is called the node of Ranvier. And so action potential would jump, okay? And so this contributes into the speed of the conduction of the action potential, okay? And so in a devastating condition where myelin is affected and the conduction of action potential is also affected as a result is multiple sclerosis. So in multiple sclerosis, it is believed that it is an autoimmune disease, okay, some hypotheses. And so the loss of myelin basically affects the conduction of the action potential, okay? And depending where the lesion is, it could give rise to different manifestations, okay? And so the properties of the action potential that we mentioned, all of it, the previous part, is the action potential that occurs in the axon, okay? What occurs in the cell body or at the level of the dendrites is called graded potential. Okay, so we have to make a difference here. Okay, so in here we know that neurons communicate via synapses, as we will learn in the next lecture. So here we have the sending neuron, this is the receiving neuron. Discharge from the sending neuron, okay, would give rise to a graded potential. And so the graded potential is a local current by, release of chemical agents like neurotransmitters and opening of the ligand-gated ion channels. Entry of sodium, okay, would give rise to the graded potential. If the graded potential was big enough and was able to reach the axon Hill lock, to bring the axon Hill lock into the threshold for opening the voltage-gated channels, this would result in the generation of the action potential. Okay? If it wasn't big enough and it wasn't able to reach the threshold, take the membrane at the axon Hill lock to threshold, this would not result in an action potential. Okay? Is this clear? You have a question? Very good. Because it's usually one discharge is not big enough to give rise to a big, current. It depends. It depends on the neurotransmitters released, the channels that are open, whether excitatory, whether it's inhibitory, as we will learn in the upcoming lectures. But what you need to understand is that the action potential is always of a constant amplitude, and it's all or none phenomenon. So it's either happens or it doesn't. Whereas graded potential, it can adds up to give rise to a bigger potential, which if it was big enough, it may depolarize the neuron, okay? So as you can see here, so graded potential is a local current, as we said. So this is the cell body. So it's receiving discharges from multiple inputs, okay? And so if the discharges were big enough to take the membrane at the trigger zone to threshold, this will result into an action potential. However, usually graded potential loses strength as it travels, okay? Because current gets leaked, okay? And so this can be described by something called the length constant, okay? Which basically means the distance where the graded potential has decreased to 37% of its original amplitude, okay? So what basically this means is that the bigger the length constant, as you can see here. So here is the site of depolarization, okay? So the bigger the length constant, the more likely that it will reach the threshold at the trigger zone to produce an action potential. The smaller the length constant, the less likely it is. Okay? Is this clear?
Doctor?
Yes.
The length constant is the amplitude?
Yes, amplitude. So the length constant represents the distance, okay? The distance where a graded potential has decreased to 37% of its original amplitude, okay? So if the graded potential was strong enough, and brought the membrane to threshold at the axon Hill lock, it will result in an action potential. If it doesn't, then it wouldn't. And so graded potential can be either excitatory or inhibitory, as we will see in the upcoming lectures. So this is just to show you again that if the stimulus was a sub-threshold, it wasn't a big stimulus, this would result in a small graded potential that is not enough, big enough to take the membrane, the trigger zone to threshold. And so this will not lead to the generation of action potential. Whereas in this case, it's a supra threshold where the stimulus was big, leading into a bigger graded potential, reaching the trigger zone, and the trigger zone was, reached a threshold for the voltage-gated sodium channels to open. Thus, we will have an action potential. Okay? So this table basically summarizes the difference between the graded potential and the action potential. Okay, the main difference is that the action potential has a constant amplitude. Okay, graded potential doesn't. It can adds up to become bigger. Okay, also mainly the action potential is mediated by the entry of sodium and the outward current of potassium. Whereas with the graded potential, it could be the entry of sodium, chloride, calcium, depending on the receptor. Okay? Usually it happens in the graded potential happens at the dendrite cell body, whereas action potential is required to be reaching the trigger zone, the axon hillock, in order to be generated. What else? Action potential, they do have absolute refractory period, whereas with the graded potential, it doesn't have refractory periods. So I hope I have done justice to the excitability property of the excitable property, electrical properties of excitable cells. Any questions? Okay, so please feel free to email me if you have any questions. Okay, specifically for people who are online. I'm happy to arrange time as well if you have questions to sit down and go over materials. Okay, thank you very much and have a nice day.
Doctor, there are a few students who have questions on Zoom.
Okay.
In the Zoom chat.
Okay. So do I have to go through the... Yeah? For neurophysiology, maybe verbs. I recommend verb. Yeah, so the reason sodium goes to the neuron because it has a huge ionic driving force that will take the its equilibrium position.
So, do you answer the question?
Yeah, this is the question. So please, to the people online, if you can send a question by email would be better, because it cannot really make sense.
I think some of them are just sort of, if you want me to go through them.
Okay.
So some of them I think is just them as just replying to you when
yeah, exactly. So please, for the people online, if you have any questions, please send it to me. Okay. Thank you. How did you calculate the ionic driving force? No, the ionic driving force is calculated by subtracting the membrane potential with the equilibrium potential for that one. So this is, let me show you, just this one is very important. So here, current equals conductance times the ionic driving force, which is between brackets, which is the membrane potential minus the equilibrium potential for that ion. For example, in the resting state, okay, we know that the membrane is negative 65, okay, and that the equilibrium potential for sodium is positive 60, okay. So you can say if we fill in here, so it will be negative 60 millivolts, okay, negative positive 65, okay, and so it will be around negative 101. And so what does this means is that when the neuron is at rest, okay, it means that there is a huge ionic driving force for sodium to go in because the sign is negative, as I said. Okay, so I hope this is clarified. This is clear. Okay, so the reason sodium goes in the neurons because it's so it will move because there is a huge ionic driving force and there is conductance. Sodium voltage gated channels are open, so conductance is not equal to zero. There is a huge ionic driving force, and so sodium will goes to the inside because of the resting state. It is negative 65 millivolt, and so when sodium goes in, it wants to take the membrane to its equilibrium potential, which is in the positive values. Okay, I hope this is clear enough.
Where is it graded? Where does that happen?
Okay, so graded potential is where what happens in the cell body and at the level of the dendrites, and it's different from the action potential, which happens in the axon. Please review the slides. I think look at the table. So the resource would be birth.
Do we have to know?
No, just know that it is 58, and the charge of the ion is important. Like if it was chloride, you have to put -1. Okay.
That's it.
Okay. Thank you very much. Thank you very much.
So I have a good question with the graded potential. If in the neuron cell body, the graded potential reaches the threshold of negative 50, is it going to spike up to positive or not?
Good question. So the graded, so I haven't mentioned this. The threshold is around positive 15 millivolts from the resting membrane.
For the graded potential?
No, so the threshold for generating an action potential. Okay. So from the cell body, because it will receive the discharge at the cell body from the dendrites. The entry of the sodium, would generate graded potential. The graded potential would add up. Because this is property of the graded potential, they can add up. If by the time, because they have to travel to reach the axon by the time they reach the axon if the graded potential has reached the threshold for generating an action potential, which is positive 15 millivolts, compared to the resting membrane potential, then an action potential would be generated.
But if it's less than 15,
if it's less, then would be no action potential will be not.
Okay, thank you.
Okay. Thank you so much.